Hello, welcome dear students. In this video, we will be discussing the second heterocyclic compound in detail, that is pyridine. C5H5N compared to benzene, one carbon is replaced by one nitrogen. The systematic name of pyridine is azine. We will be discussing preparation as well as properties of pyridine. Starting with preparation, we have three methods of preparation. The first one, pyridine prepared from acetylene and hydrogen cyanide when taken in 2:1 molar ratio, 2:1 molar ratio, and passed through red hot tube. What happens here? The two acetylene and one HCl molecule undergo cyclization like this. A rearrangement of bonds giving pyridine. Okay. The second method is from pentamethylene diamine. This is pentamethylene diamine or pentane 1,5-diamine. 1, 2, 3, 4, 5. It's pentane basically, and two amino group at the ends, and we have taken the hydrochloride. Okay, hydrochloride of the amines. So that's why it is NH3Cl. This on heating will lose two molecules. One is ammonium chloride is lost, also HCl. So this is what's happening. NH3Cl will take one H from here, NH4Cl, and one HCl is also lost, and you get this one, the intermediate product. What is this compound? This is a saturated analog of pyridine. Pyridine, when fully saturated by adding hydrogen, it becomes this. This is called piperidine. Okay? Piperidine, which is an essential constituent of the alkaloid obtained from black pepper, that's called the piperine. Piperine contains this piperidine heterocyclic ring. Now this, on further heating with palladium charcoal catalyst and heating, it will lose hydrogen. It loses 3 molecules of hydrogen. That means it's a dehydrogenation or aromatization and becomes pyridine. The third one, from pyrrole we can prepare pyridine. Pyrrole is treated with dichloromethane in presence of sodium ethoxide and heating. This methylene group get inserted into this ring and become pyridine. So these are the 3 methods of preparation of pyridine. Now we move on to the properties, starting with structure. Like we discussed in the previous video about furan, here also we have 2 aspects to discuss in structure. The first one is the resonance concept. So what is the resonance structures of pyridine? It's very important in explaining basicity, similarly the reactivity, orientation, etc. Now look at this, how we draw resonance structures of pyridine. What happens is that, see, nitrogen has a lone pair. Now this pi bond shift to nitrogen, and we get the second structure. What do you get? You get a negative charge and lone pair, isn't it? Due to shifting of this pi electron, and this becomes positive. This carbon become positive, and now this will repeat. This pi bond will move to get the third structure. Okay, positive charge now appear here, and there is negative charge and lone pair. The next moving this one, you get positive charge now over here, and finally this lone pair is shifted, giving the last structure. So as usual, here also we have 5 structures altogether. Out of these 5 resonance structures of pyridine, the first one, the last one are chargeless, neutral, no charge, and these are like the kecyl isomers of benzene, changing the position of the double bond. These 3 are carrying charges. Charge separation is there, and these structures are important in explaining basicity, reactivity towards electrophilic and nucleophilic substitution, and the orientation. So these structures have to be kept in mind for further discussion. Let it be there. And regarding resonance, we know resonance increased stability. The resonance stabilization energy of pyridine is found to be minus 125 kilojoule per mole, which is found to be more than that of benzene, even more stabilized due to resonance than benzene. Okay. Now the next one is the hybridization structure. Hybridization of pyridine. What is hybridization of pyridine? Hybridization state of pyridine. That means all the 5 carbons and nitrogen all are in sp2 hybridization. Remember that. All in sp2 hybridization. See, if you take carbon for example, the excited configuration is 1s2, 2s1, 2px1, py1 and pz1, and this is what is happening. sp2 hybridization takes place, and 1p pz is left out of hybridization, that is kept for lateral overlapping to form pi bond. If we draw the sigma orbitals, overlapping of hybrid orbitals, see, suppose this is nitrogen. Okay. Now, if you take one carbon for example, each carbon is in sp2. So you have one sp2 hybrid orbital here, the second one here, and the third one here. So on each carbon, 2 hybrid orbitals will be overlapping with the neighboring carbon, forming carbon-carbon sigma bond. And on each carbon there will be one sp2 hybrid orbital, the third one, containing 1 electron, which will overlap with what? Oneness of hydrogen. Now on nitrogen also it is sp2 hybridization. So this is one hybrid orbital, this is the second hybrid orbital, containing 1 electron each, forming sigma bond with carbon, and the third hybrid orbital contain 2 electrons, that is the lone pair. This lone pair is present in sp2 hybrid orbital. Remember that. Now on each carbon as well as nitrogen, 1pz is unhybridized. We can show the pi orbital formed like this. So this is the sigma bonds for sigma orbitals. Now the pi orbital is formed by the unhybridized orbital on each carbon as well as nitrogen, which all contain 1 electron each, like this. Okay. So what happens? They undergo lateral overlapping, forming pi bond, isn't it? So you will have, just like in furan, the sigma skeleton or the planar ring will have a pi lobe, one above the plane and one below the plane. So it is pi electron rich, exposed, so it is attacked by electrophiles. Pyridine undergo electrophilic substitution reactions. We will see that later. Now pyridine is aromatic because it has the complete cyclic conjugation. If you apply Huckel rule, 4n plus 2 pi, 4n plus 2 rule, so this contains 4n plus 2 pi electron where n is equal to 1, so it is 6 pi electron. Which are they? You have the 3 pi bonds, that's the 6 pi electrons. Remember that in pyridine, this lone pair is not involved in the delocalization. It is free. It is freely given, or it is fully available for donation. That means pyridine acts as a good Lewis base. Okay. We will now go to the next one, the remaining properties. The next one is basicity. Okay. As I told you, pyridine is highly basic, quite basic. pKb value is 8.8, which is comparable to that of aniline. Okay. Now, how to explain the fairly good basicity of pyridine? As I told you, the lone pair is fully available for donation, and this can be contrasted with pyrrole. You know, pyrrole we discussed earlier, which has a lone pair, and comparing basicity of pyrrole with pyridine, which is more basic. Pyridine is more basic. Why pyrrole is less basic? Because this lone pair is involved in the delocalization to attain aromaticity. But in pyridine, this lone pair is not required for attaining aromaticity. Okay, so this is fully available for donation. And again, if you look at the resonance structures, you can see that these three structures contain negative charge on nitrogen. What does it indicate? Negative charge on nitrogen indicate that nitrogen is electron rich, so it can donate electron very effectively. Now, to illustrate the basic, and one more point is, if you compare basicity of pyridine with aliphatic amine, for example, RNH2, let me write aliphatic amine, which is more basic. Aliphatic amine is more basic than pyridine. How do we explain? This can be explained on the basis of the nature of hybrid orbital which carries the lone pair. I told you that this lone pair on pyridine is present in what? In sp2 hybrid orbital. Whereas in aliphatic amine, this nitrogen is in sp3 hybridization. Okay, so the lone pair is in sp3 hybridization. So what? You know that sp2 hybrid orbital having more percentage S character is more electronegative. That means it holds electron tightly compared to sp3 hybrid orbital. So donation of lone pair is more difficult in pyridine than in aliphatic amine. Okay. Putting example for this basicity, if aniline, if treated with HCl, what happens? Using the lone pair, it forms the salt. You get pyridinium chloride. Okay, so this H plus get attached here, and it become plus and Cl minus. What is this called? Pyridinium chloride. Another reaction is, if we treat with CH3I, methyl iodide, this get attached to nitrogen, forming a quaternary ammonium salt, that is N-methyl and there will be a positive charge here and I minus. N-methyl pyridinium iodide is obtained. Both these reactions illustrate the basic character of pyridine. Okay, now next one. Two important reactions coming here. Electrophilic substitution reaction as well as nucleophilic substitution reaction are known for pyridine. First of all, electrophilic substitution reaction. We know that any aromatic system having which is rich in pi electron is attacked by electrophiles and undergo electrophilic substitution reactions just like benzene. Two questions comes when you talk about these substitution reactions. One is what about the reactivity, and second one, what is the orientation? We see that when we consider the reactivity of pyridine towards electrophilic substitution reaction, it's found to be less reactive than benzene. Less reactive than benzene. Okay? Between pyridine and benzene, pyridine is less reactive than benzene towards electrophilic substitution reaction. How do we explain? Because this electronegative nitrogen is withdrawing electron towards it and reducing the electron density on carbon. See that electrophile has to attack the carbon, not nitrogen. So reactivity is reduced. Now regarding orientation, see there are three different positions. Compared to this nitrogen which is position 1, this is 2, this is 3 and this is 4. This is again 3, this is 2. So there are three different positions. Preferably attack takes place at position 3 for electrophilic substitution reactions. How do we explain? In two ways we can explain. One, looking at these resonance structures, you can see that in these structures there is positive charge appearing at position 2 as well as position 4. What does it mean? At these positions 2 and 4, electron density is particularly reduced. That's indication of positive charge. So electrophile will preferably attack which position? Position 3, where there is no positive charge. This can also be better explained in another way. That is, you consider all possible attacks and consider the intermediate and compare the stability. Whichever gives more stabilized intermediate, that will be the predominant product. If the attack is at C2, suppose it is here, what happens? So you see, electrophile is coming plus E plus. Suppose E plus is electrophile, so it will attack. It is attacking here. That means using this bond, it will attach here. Let me show the hydrogen. Hydrogen is there everywhere. So what you get? The first structure will be using this bond. It form the bond with E and H is there. So H and E. So what happens? On this nitrogen appears a positive charge because this electron is lost from here. And remaining bonds are here. Now resonance stabilization. Bond shift here. You get the second structure. It is now double bond here. And then positive charge is now here. And finally, this will shift to this position. You get the third and final structure. Okay. It is now like this, plus here. These are the three structures. Now let us consider if attack is at position 3. If attack is on this carbon, then what are the resonance structures of the intermediate? What is the intermediate form? You get now here electrophile is attached. Actually it is using this bond, so when this bond is used up, positive charge will be appearing here, correct? This is there intact, this is also there. Now shifting, this will go. What happens? You get like this. Positive charge is here And then shifting of this one, you get the last structure. In here, double bond here as well as here, positive charges here. These are the structures obtained for attack at C3. Now finally, attack at C4. If attack is here, positive charge will be appearing here. So the structures are now H and E. Positive charge is here now. Then double bond is here. Shifting of this takes place. Getting the next structure. Okay. Positive charge is now appearing on this nitrogen, and then this is moving, getting the third structure. So what do you get? You have it now here, and positive charge is here. Okay. So we got three structures which are resonance stabilized for each attack. Compare the stability. Whichever attack give more resonance stabilized intermediate, that attack is preferred. You can see that attack at C2 and C4 is giving structures where positive charge appears on nitrogen. See, look at this. Positive charge is here. Here also there is positive charge on nitrogen. But you can see in this structures, there is no positive charge appearing on nitrogen. So what is that point? When positive charge is on nitrogen, it is very unstable. See, nitrogen is an electronegative atom. It can very well hold a negative charge, not a positive charge. So these structures are comparatively less stable than these structures. So attack at C3 give more resonance stabilized intermediate. So C3 is the preferred attack. So orientation is C3 for pyridine for electrophilic substitution reactions. Okay. Now we can take example. A few reactions to illustrate this. Only three we have. Nitration, sulfonation and chlorination. So let us take three reactions. Nitration using nitrating mixture, concentrated nitric acid and concentrated sulfuric acid at little high temperature. What you get? You get nitropyridine where? Position 3. So you have NO2 here. So this is 3-nitropyridine. When treated with fuming sulfuric acid, okay, fuming sulfuric acid in presence of little amount of HgSO4, which may catalyze the reaction, and you get sulfonic acid group attached at position 3. So what's the name of this compound? Pyridine 3-sulfonic acid. Finally, chlorination is using chlorine in presence of AlCl3, that is a catalyst here, giving 3-chloropyridine as the product. 3-chloropyridine. Okay. So we have three examples for electrophilic substitution reactions. Next we have nucleophilic substitution reactions shown by pyridine. See, interestingly, pyridine is quite reactive towards nucleophilic substitution reaction. How do you compare with benzene? We know benzene generally undergo electrophilic substitution reaction, but when benzene is connected to electron withdrawing groups like nitro group, etc., you might have learned this one. Nitro group, which is withdrawing electron, make benzene ring electron deficient and susceptible for nucleophilic attack. Similar thing happens in pyridine. Why? Because of this nitrogen. You know, nitrogen is highly electronegative. It is withdrawing electrons, okay, and make the ring a little bit electron deficient, so nucleophiles also attack pyridine. Pyridine undergo nucleophilic substitution reaction. Again comes the two questions. What about the reactivity? What about the orientation? What about the orientation? Again, looking at the resonance structure, we can predict. See, in these resonance structures, you can see that positive charge appear on position 2 as well as position 4. Correct? That means what? Position 2 and 4 are particularly electron deficient. So naturally, nucleophile will be preferably attacking 2 as well as 4. So contrary to electrophilic substitution, orientation is C2 and C4 here, whereas in electrophilic substitution it was C3. We can also explain this point using resonance structures. Let me put one example at least. See, for example, if attack is at C2, okay, attack is at C2, for example, nucleophile, let us show it is Nu say minus, which is attacking. So if it's attacking here, see, this is already having a lone pair using which it formed the bond. So the first structure appearing will be like this. See, at this position, H and nucleophile is attached using its own lone pair. So what happens, this will be shifting to nitrogen. So it becomes negative charge on nitrogen, isn't it? And the remaining ones, the bonds are here. And the next structure, this will be shifting, this will be moving to this carbon. You get the next structure, that will be double bond here and negative charge here, and this double bond here. The next will be, this is moving, you get the third structure, that is, you get now double bond here and negative charge here. You get three structures here. Similarly, if you try C3, you get three structures. C4, you get another three structures. We have seen that attack is preferred at C2 as well as C4, not at C3. How do we explain it? In this structure, you can see negative charge appearing on nitrogen. Okay. In C4 also, you will see negative charge appearing on nitrogen, which is more stable, more favorable, because nitrogen, being an electronegative atom, can very well hold a negative charge. Whereas if you consider attack at C3, you can see that there is no negative charge appearing on nitrogen, whereas negative charge is appearing only on carbon. So carbon carrying negative charge is not very favorable. Carbon is not very electronegative to hold effectively a negative charge. So that's how we explain it. We go to a few examples for nucleophilic substitution reaction. Okay. Look, a few reactions we take. First one is treated with sodamide, all at a little high temperature of the order of 100 degrees Celsius. What happens? Na plus and NH2 minus. So this is the nucleophile which get attached on C2. See, between C2 and C4, we have seen that C2 and C4 are preferably attacked, and out of that, C2 is still more preferred. It is more predominant substitution takes place at C2, maybe because this minus the effect of nitrogen is more on this C2 position than at C4 position. So that get more electron deficient, so that nucleophile attack the, what is this product? This is 2-amino-pyridine. The next one is treating with KOH, potassium hydroxide. So the nucleophile is OH minus. You get, what do you get? You get 2-pyridanol, isn't it? You get pyridanol, 2-pyridanol. Okay. And this one undergo tautomerization. It can undergo tautomerization, giving a structure like this. There is pyridine you get. This become double bond. See, shifting of this bond can shift here, and this one here, and H get migrating to this nitrogen. So this is called 2-pyridine. And one more is there, that is tertiary butyl lithium C4H9Li. Not tertiary butyl, this is N-butyl lithium we have discussed earlier, which is an organometallic compound, lithium compound. Normal butyl lithium can react with this, and this position to get substituted by this N-butyl group like this. Okay, so you get 2-butyl pyridine. If it is phenyl lithium, you get 2-phenyl pyridine. Very similar reaction. So these are nucleophilic substitution reactions. Now finally we have a few reduction reactions. See, pyridine can be reduced using various reducing agents. Okay, you can add hydrogen, and there are different reaction products using different reducing agents. See, you can use, if you are using a usual catalytic reduction using hydrogen in presence of nickel, or sodium in ethanol, etc., complete reduction takes place. Addition of 3 hydrogen giving what? What do you get? You get this one, that is, I told you earlier, piperidine. All the pi bonds are broken. Now, if reducing agent used is LaH or lithium aluminum hydride, interestingly, partial reduction takes place. Only this bond get broken. So it's a selective reduction actually. So what you are getting, this bond is broken with hydrogen. So 1,2 positions get hydrogenated. This is known as 1,2-dihydropyridine. 1,2-dihydropyridine. And if the reducing agent is sodium in liquid ammonia, again reduction is partial, but now it is 1 and 4. Actually this reaction is called Birch reduction, which you might have learned in 4th sum organic in the reduction of benzene, a very similar reaction. So these 2 positions are reduced. Okay, so you get the product as like this. This become NH, and this is also hydrogenated, reduced. So 1,4-dihydropyridine you get. Finally, if you are treating with HI, okay, exhaustive kind of reduction, the ring is opened and it is cleaved. What do you get? You know, you get a pentane, that is the 5-carbon aliphatic chain, CH3, CH2, 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 CH3, and this N is separated as ammonia. Okay, so it is a total cleavage takes place, and the ring rupture takes place here. So these are various types of reduction. So it's a versatile chemistry of pyridine. With this we come to end of the discussion of preparation and properties of pyridine. Thank you.